Today we are going to explain a new chapter, which is interference of light. First, we are going to explain what is interference. Interference is the superposition or the meeting of waves coming from synchronous and coherent sources. Interference is the superposition or meeting of waves coming from synchronous and coherent sources. Synchronous sources are sources emitting waves of the same frequency. Coherent means that the phase difference between the sources is constant. So what does coherent and synchronous actually mean? Consider the sources S1 and S2. Assume that the sources produce sinusoidal waves, having the expressions S1 equals to A sine omega t plus phi 1 and S2 equals B sine omega t plus phi 2. Omega is equal to omega in both expressions. So the sources are synchronous, where omega is equal to 2 pi f. Phi 1 is the initial phase of S1 and phi 2 is the initial phase of S2. The phase difference between the two sources is the difference between the phases, which is, for example, delta phi equals phi 2 minus phi 1. If the answer is constant, the two sources are said to be coherent. The two sources are synchronous because they have the same omega, and coherent because the phase difference between the two waves is constant. If phi 1 and phi 2 are both constant, obviously, the difference is constant as well. How can we fulfill the conditions of two sources being synchronous and coherent? For the interference phenomenon to take place, two conditions must be satisfied. The two sources must be synchronous and coherent. So how can we achieve these conditions? The two sources, S1 and S2, can be the images of a common source S. For example, when looking at the interference of water, the vibrator is equipped with a two-tip source. These two sources barely touch the water surface, and the vibrator is set to operate at a frequency f. This means that the two tips S1 and S2 that are barely touching the water surface vibrate at the same frequency f. And when the vibrator moves up, S1 and S2 both move up at the same time. And when the vibrator moves down, the tips S1 and S2 move down as well. As a result, S1 and S2 are the images of the main source, which is S. S1 and S2 have the same frequency as the main source S. S1 and S2 move together as a group. So we say that these two sources vibrate in phase. Hence, the phase difference between the sources is always zero. That is to say that the phase difference between S1 and S2 is constant. S1 and S2 obey the interference conditions. Synchronous sources, because they vibrate at the same frequency. Coherent sources, because their phase difference is always constant. In our chapter, we will talk about interference of light. So how can light satisfy the above conditions of interference? For this, consider a screen on which we make two very small openings of widths less than 1 millimeters. And let's bring a light source S that emits a monochromatic light, which means that it is formed of one frequency or one color. The source S illuminates this screen. We notice that light leaves the two openings spreading out, as we saw in the previous chapter, diffraction. The light coming from the source S1 and the source S2 will superpose in this region. And as a result, S1 and S2 are the images of the main source S, and therefore these two sources are synchronous and coherent, which means that they obey the conditions of interference. This is the region of the superposition of the two diffracted beams coming from the sources S1 and S2. In this region of interference, or the field of interference, where interference takes place, interference region, we place an opaque screen, or simply an observation screen. Here on the screen, we observe the interference figure. The two other regions, interference doesn't take place, only the common region where the two diffracted beams meet. We can show the evidence of the interference phenomenon by performing Young's double slit experiment. Young's slits are two very thin slits that are very close to each other, that are found in the same plane or same screen. In Young's experiment, we illuminate the two thin and close double slits by a monochromatic light source and place, at a certain distance from the plane of the slits, an observation screen. Now we are going to demonstrate Young's experiment. This set contains three Young's double slits. Notice how close each of the double slits are. Here we have very close and very thin rectangular slits. The distance between the two slits is 0.25 millimeters. This one, also observe, they are very thin and very close, separated by 0.3 millimeters. And the last one is clearer. The two thin and close slits are separated by a distance of 0.45 millimeters. We're going to illuminate each of the double slits by a laser, then observe the obtained figure on the screen. When switching the laser source on before introducing the double slits, we observe a spot which corresponds to the laser beam. Now we're going to introduce Young's double slits in front of this beam. We observe alternating and equidistant bright and dark spots. These spots are called the interference fringes. When Young's slits are aligned horizontally, the interference pattern will be aligned horizontally as well. Whereas if the slits are aligned vertically, the interference pattern will be aligned vertically as well. In Young's double slit experiment, we observe on the screen alternating dark and bright fringes. Now we want to interpret the formation of these fringes. Let M be a point at the center of a dark fringe. What is the reason for the formation of a dark fringe? S1 and S2 are two synchronous and coherent light sources, since they are the image of S. S1 emits a wave that reaches M, similarly S2. If the waves that come from S1 and S2 superpose in opposite phase, the luminous intensity at M will be 0. Thus M is a dark point. If the vibrations coming from S1 and S2 reach another point N in phase, the amplitude of the luminous vibration at N will be maximum. Hence, the luminous intensity at N will be maximum as well. As a result, N will be at the center of a bright fringe. This is the interpretation that showcases or highlights the wave aspect of light. Since this and the diffraction experiments, along with many other more experiments, show that light behaves as a wave.